I have the privilege of serving as a John and Adrienne Mars Director of the Smithsonian's National Air and Space Museum. Welcome to tonight's Exploring Space lecture. Tonight's program is the third in a series of 4 programs examining the realities of living and working in space for years at a time. First, we looked at studies conducted at remote bases on Earth. Then we turned outwards to the International Space Station. And now tonight, we're joined by NASA's Chief Exploration Scientist, Dr. Jacob Bleacher, to hear about future bases on the Moon and Mars. And you won't want to miss next month's final lecture when we go even further afield and look at the habitability of Saturn's moon Titan. That program will take place June 29th, both in person here at the museum on the mall here in DC and live on YouTube. You can sign up to attend on our website. Before going any further, I'd like to extend our sincere thanks to the sponsors of the Exploring Space lecture series. Tonight's program is made possible through the generous support of Aerojet Rocketdyne and United Launch Alliance. Joining us in the audience tonight are Mary Angola, Joe Cassidy from Aerojet Rocketdyne, and Brandon Eden from United Launch America, or United Launch Alliance. Thank you, Mary, Joe, and Brandon, for your ongoing support. To those of you joining us in person, I hope you had the chance to take a look at the Destination Moon and Kenneth C. Griffin Exploring the Planet's galleries before tonight's lecture. These spectacular new exhibitions are 2 of the 8 galleries that we opened here at the museum in DC last fall, and we are pleased to share them with you as part of tonight's exploration of human spaceflight and planetary science. And as an aside, since opening these 8 galleries last October, over 1 million visitors have come into the museum, so they've proved immensely successful. As you have noticed when you did enter the building tonight, our renovation continues, and there is still plenty to see at the museum, including many new artifacts. In fact, over half of the artifacts on display in our new galleries are in the museum for the first time. And of course, we'll have even more for you to explore as the new galleries open on the other end of the building in the years to come. Now I'd like to turn it over to my colleague, Dr. Ross Irwin, chair of the museum's Center for Earth and Planetary Studies, to introduce tonight's speaker. Ross?
Thank you, Chris. It's a real privilege and a lot of fun for me tonight to be able to introduce our distinguished speaker. As a friend of mine, Dr. Jacob Bleacher, Chief Exploration Scientist at the Exploration Systems Development Mission Directorate at NASA headquarters. He advocates for science in the human exploration of the Moon and Mars, and he coordinates with NASA's Science Mission Directorate and the planetary science community, imparting a unique combination of wisdom and sometimes tough love. Dr. Bleacher's research focuses on the volcanic history of the Earth, Moon, and Mars. He has examined potential landing sites and developed science traverse strategies for them. He was a science team member and test subject on NASA's Desert Research and Technology Studies, or Desert RATS program, which tested operations for prototype human rovers that would be used on the Moon. He has applied his expertise to field studies, advising NASA on lunar sample acquisition, science objectives, astronaut training, and the use of resources that are available on the Moon and Mars. Dr. Bleacher earned a Bachelor of Science in Geosciences from Franklin and Marshall College and a PhD in Geological Sciences from Arizona State University. After he speaks, we'll have time for questions and answers, so please feel free to submit your questions online or remember them to ask here at the microphone in the room. Very grateful to our sponsors, Aerojet Rocketdyne and United Launch Alliance, for making a series like this possible. And thanks to all of you for joining us tonight to learn about exploring the Moon and Mars learning to work and live in space.
Thank you, Chris and Ross. It's a pleasure to be here. Thanks to the Smithsonian, United Launch Alliance, and Aerojet Rocketdyne. Opportunities to talk about the exciting work that we do inside NASA are opportunities we like to take advantage of. Sometimes it's easy to forget that people who aren't doing this every single day don't know all the details that we do. And there's so many cool things we're doing right now. I mean, you look at the title here, Exploring the Moon and Mars, Learning to Work and Live in Space. That's amazing. I mean, it's tremendous to take part in this. The Smithsonian Institution giving us this opportunity. You know, when I got here today, first of all, my wife and I went up to Destination Moon and looked at the Lunar Reconnaissance Orbiter hanging there. We used to work at Goddard Space Flight Center. Remember watching that spacecraft come together, knowing that it would acquire data of the lunar surface that would help us plan where astronauts would go in the future. And to now be taking part in actually planning that out is just, it's tremendous to take part in that. I also remember as a small child, my parents brought me here to this very museum, and I have this clear memory of seeing the Voyager spacecraft hanging from the ceiling, being told, yeah, that's going out to the outer reaches of the solar system, and it's now outside of the solar system. And I remember that having a huge impact on me, thinking about this thing that we built that is going to go so far away from our home here on Earth. And it's really a key part of exploring and learning to live in space. Now, one thing I did want to say before I get started here, we've been talking over the last several years about the Artemis generation, the future generation that will be the Artemis generation. And I just want to say that everyone in this room right now and everyone who can hear me online at this moment is now truly a part of the Artemis generation. We launched Artemis 1 last year, late last year. That makes all of us part of the Artemis generation. We're going to the moon, and we're looking at going beyond the moon to Mars. And a big key to that is learning how to survive out there. And so that's what we'll talk a little bit about today. But first I'm going to start with a short video just kind of recapping that Artemis 1 activity. So if we can cue up the video, please.
Our return to the moon will be different than the last time. We plan to explore more of the lunar surface and
The
learn
space
how
launch
to
system
live.
is now counting down to liftoff of Orion on its maiden voyage to the moon. And here we go. Hydrogen burn-off igniters initiate. 7, 6, 5. 4-stage engine start. 3, 2, 1. Boosters in ignition. And liftoff of Artemis 1. We rise together back to the moon and beyond.
We are all part of something incredibly special, the first launch of Artemis.
This view of Earth from a human-rated spacecraft not seen since 1972 during the final Apollo missions.
Distant retrograde orbit. We're going to be about 38,000 miles away from the lunar surface. We're going beyond anywhere we ever went for Apollo.
The Orion spacecraft is barreling its way back home after circumnavigating the moon and beyond in an elliptical distant retrograde orbit. Splashdown. Orion back on Earth.
So I don't know how that makes all of you feel, but that still gives me goosebumps seeing that space launch system carrying the Orion off the surface of the Earth up towards the moon. It just is such a tremendous thing to witness. I hope that you all will get to witness one of the future Artemis launches, even if you got to see the first one. It's just something to see. It's important to understand what we're motivated by. This comes from the United States Space Priorities Framework, and I like to start here. The United States will maintain its leadership in space exploration and space science. I think it's really important those two words, exploration and science, are linked in that sentence. That's what we're doing. We're exploring and we're doing science. They're intimately linked with each other. Science is kind of the backbone around which we develop our exploration systems. We don't just go somewhere to do some science. The scientific knowledge that we've already gained about the moon, for instance, from the Lunar Reconnaissance Orbiter, is that backbone that helps inform us how to build the hardware, the technology, the systems that will enable us to go learn to live and work in space. Right now, NASA is undergoing an activity we call the Moon to Mars Goals and Objectives. Basically, what we're doing is developing a blueprint for how we explore our solar system. This will be our approach that we use and have used in low Earth orbit, extending to the moon, to Mars, and beyond. We interacted with the community, the public across NASA, industry partners, international partners, other agencies within the United States, to try and understand why they want to go somewhere else. Why would you want to go to the moon? Why would you want to go to Mars? Collecting that data helped us begin to bend those objectives into groups. In some cases, there's recurring tenets, something that most everybody brought up. This is something we would need in order to go do the objectives we want. But there are big other bins: science, transportation and habitation, building the infrastructure that will enable us to live off the Earth, and then general understanding of the operations. How do you do that work once you get there? There's a QR code on there that you can look at to see the information that we've collected so far. And now we're in the process of taking those goals and objectives and starting to break them down and to understand what kind of capabilities and needs do you have in order to do that, to meet that objective. This is an ongoing process for us. And it's one that will enable us to design our architecture, design our systems in a way in which we say, what do you want to go do, so that we can figure out what are the right things to build to make that happen. So this is the process that will help us partner outside of NASA, globally, in order to go live off the Earth. But what are the benefits to humanity? Why do we explore? Well, we like to talk about these in kind of three broad areas. There's science, there's inspiration, and there's national posture. So the types of research that we would do, understanding how humans respond to the space environment, biology, astrophysics, heliophysics, planetary science, physical sciences. These are all the activities that we would hope to be doing as the objectives that we go out there. But we're also looking to inspire. Why would you go do these bold things if there's not someone to pick up that torch after you're done doing your job? And so we want to see the next generation carry this on. And so we need to be inspiring as we move along. And then national posture, our global influence, our international relationships. NASA can't do this alone. These bold endeavors to go live off the Earth, they're not something you can do by yourself. And so we need that partnership. We lead and then we partner so that we can realize these lofty goals. So we'll talk a little bit about where we are now and where we're going. And I know that if you were listening to the other lectures in this series, you've heard a little bit about the International Space Station. And I tried to think a little bit before I came here about this question about going to live away from the Earth. And it's actually really a fundamental core piece of really the human soul. From the time you're born, you're learning how to live in new environments. I don't know if my childhood was a typical one, but I I grew up with a family here in the United States, and I lived with my parents, and I spent time increasingly away from them. I first started spending weekends maybe with my grandparents, aunts and uncles. Eventually that evolved into spending sleepovers with friends' families. So we had goals and objectives there too. I wanted to not waste any time playing with my friend, and the easiest way to go and meet that objective was to actually be in the same place, the place where you want to do that work. So learning to live away from the environment that I understood was just a key part of growing up. And I think it's that way for pretty much all of humankind. And it's no different than trying to live away from the earth. The earth is where we start, it's where we learn, and we use the lessons we learn here on earth to help us understand how to survive farther and farther away. So the first step for us away from the Earth was learning to live in low Earth orbit. So the International Space Station has been a home away from home for astronauts for over 20 years, continuously. We have had astronauts occupying that space station for more than 20 straight years. That has taught us many lessons about how to survive off of the Earth. Now, the reason we start so close is because if there's a problem, we can come home. We can send supplies. We can support them there. But just like spending time at my grandparents, followed by spending time at my friends' houses, we're ever looking to that next step. What can we do next that will be exciting, that will be a challenge? What goals do we have that require us to go farther? Now, of course, going into Earth's orbit provides us an opportunity to learn more about our home. So this is a really key thing to understand. When you go live away from the Earth, you're not simply leaving the Earth. You're learning more about the Earth. Everywhere we go, we learn more about ourselves. We learn more about our home planet, the Earth, and really how delicate and fragile it is. We learn about what the environment is like today, where it's trending, maybe how to protect it. These are some examples of spacecraft that have been flown into low Earth orbit as well. So not only are we sending our astronauts there, but we're sending spacecraft there to help us understand our environment. So learning how to live and work in space, again, helps us understand more about our place here on Earth. Now, I talk about going far away helps you learn more about where you are. One of the great things about challenging yourself to go into environments that are maybe difficult compared to what you're used to is that you have to come up with very creative mechanisms, techniques, hardware, technology to help deal with these constraining environments. And the challenges that NASA is given to live, work in space yield significant return here on Earth. And so we have a tremendous amount of data showing what feeds back into life here on Earth. I love this slide. It shows a few examples, and probably everyone who presents this that works for NASA or works with NASA has their own favorites. I love the one at the top left. Baby formulas in 65 countries use NASA-developed algae-based food supplements. When you're trying to live in space, you don't have a plethora of food available to you anytime you want it. And so you have to learn how to maximize what you have to the benefit of supporting the people that are there. And so those lessons learned feed back into our life here on Earth. They teach us more about where we come from and how to survive. Another one that I like is thinking about water. Water is very heavy, and it is very clear that you don't want to use water one time and discard it and then bring more water off the surface of the Earth. And so we have developed systems to recycle, reclaim water. And that's how we operate on the International Space Station right now. That's the type of technology that can have tremendous benefit here on Earth. And we're creating it because we have to. We have to do it to meet the challenges that we've been given, surviving and working out in space. Another thing that's great about it is learning to work internationally. You may be aware that we have had international partners. It's called the International Space Station. We often fly with our international partner astronauts to the space station where they go to do their work as well. Also, the industry partnership. So for low Earth orbit transportation right now, our astronauts are riding on vehicles that are not built by NASA. So we are developing an economy in low Earth orbit where companies are flying our astronauts to orbit. They're also flying other people to orbit. So they are developing now an economy for themselves that's supported in part by what NASA needs from them, but also what they can gain from it. So how are they learning to, profit from spending time and going into low Earth orbit? And what this enables us to do at NASA is start to look a little bit farther out. Now that we know we can depend on partners to get our astronauts up to the space station, we can think about what will it take to actually get our astronauts to other places like the moon. Also back here on the Earth, we're starting to prepare. What is it we're going to do when we get out to these other destinations? One thing that I really enjoy that I get to take part in is training our engineers and managers, as well as our astronauts, how to do the kind of work on the surface of the moon that we would expect them to be doing when they get there. One of those fundamental things we expect to do is geology, studying the moon itself, just like we study the Earth here back here at home. And so these activities they're enjoyable, but they help all of our different engineers and managers start to understand what the job will look like when they get to another destination like the moon. So to the moon, that's where we're going, right? You should all be familiar with the moon. At nighttime, you can see it, right? It's one of those celestial things that you can see. It's right up there in the sky. It changes in a predictable manner. I'm sure you've probably seen it. Sometimes it looks like this in the picture. Sometimes it's a full moon. Sometimes you can just barely see it. It's going through cycles. We have to understand those cycles in order to be able to travel there and live on the surface of the moon. Science is what teaches us how to understand that environment. With that science, then, we can begin to build the systems. And really what it comes down to then is partnering to go and explore the moon. True to its name, Artemis, which is the set of missions that we have named to take our astronauts to the moon, it's focused on promoting mission equity, and we'll be sending the first woman and first person of color to the moon with the Artemis missions. And in fact, with Artemis 2, first woman and first person of color will actually orbit around the moon. So this is an exciting time. This is what it's like for humankind to go and explore the moon, internationally, with industry partners, working together to get those jobs done. There we go. Now, as I said, we have to learn and understand how to operate in that environment. It's, in many ways, we think about it, it's a very hazardous environment, okay? That's why we have to build things like suits and spacecraft. But it's no different than here on Earth when you travel long distances, or maybe you want to see what's on the bottom of the ocean. Or if you're like me, you want to see what's going on in volcanoes, which are very hot and sometimes inhospitable. You have to design systems to help keep you safe and protect you, and you have to understand that environment. Before we can spend long periods of time in space, especially away from the Earth, even beyond low Earth orbit, we have to start understanding the hazards to our astronauts. We have to deal with things like space radiation. In low Earth orbit, we're still protected by the Earth's magnetic field. Learning to operate in isolated environments and confinement. So what is it like to be operating in small crew capsules for long periods of time? Just in general, operating at distance from the Earth. Like many of us, you probably know what this is like if you've gone away from home for periods of time. I know when I left, I grew up on the East Coast in Pennsylvania, and when I went to Arizona State University, that was a long way from home for me. And so you do run into periods of time where maybe it's, you're sad that you're not around your family as much as you'd like. It's no different if you're operating off the Earth. You're going to be away from everything that you're familiar with and that you know. Right along with that is trying to operate in a place with no gravity. We know what it's like to operate in no gravity in low Earth orbit, but we will be spending more and more time as we go out into the solar system in that low gravitational environment. And then just in general, dealing with hostile closed environments. So we create our own ecosystem inside of a spacecraft, and learning how to deal with that. We're learning how to deal with it at the ISS, where again, I already said that it's nice there because we're not too far away from the Earth just yet. But you can imagine going to a place like Mars, which can be many months of a one-way trip just to get there. You have to understand how your systems are working so that you can make sure you're protecting your astronauts. So starting to understand how our astronauts will respond to that environment, we're starting to plan out the series of missions to at least get us started on this path. And so I referred to the Artemis missions. The video we watched at the very beginning, Artemis 1, is now a completed mission. And that's why we can all say that we are part of the Artemis generation now. So that was a test flight of the SLS, Space Launch System, with the Orion crew capsule. So that's the capsule that will carry our astronauts. And our Exploration Ground Systems, or EGS. We're planning the Artemis 2 flight in 2024, and this will be a very similar mission to Artemis 1. The Orion crew capsule will go around the moon, but it will be carrying our astronauts this time. So that will be the first flight of astronauts out to the moon in 5 decades. Artemis 3, we plan for 2025, would be a crewed mission, and now we're looking at landing on the surface of the moon in a place we've never been, the South Polar region of the moon. So now including the Space Launch System, Orion, the EGS, Exploration Ground Systems, we now have something called the Human Landing System. And I'll talk a little bit more about that as I talk in more detail about these missions. Artemis 4, we will be at the point where we're starting to build a small station that will be orbiting the moon and supporting our activities on the lunar surface. This is called the Gateway. The Gateway will now be a destination where our spacecraft can take our astronauts to before they take that last trip down to the surface of the moon. And now, where this is different from Apollo is that we're starting to develop our systems more specifically to take advantage of smaller parts of the trip. So Apollo, the spacecraft went from the Earth to the surface of the moon, back to the surface of the Earth. And as we start to break that down, I like to call them legs. There's several legs to that trip. There's going out to the lunar vicinity from the Earth, and there's going from the lunar orbit or lunar vicinity down to the lunar surface. So you can start to design systems that are optimized or just doing one part of that job instead of trying to do the whole job at the same time. And that's kind of the approach that we're taking now. So we can work with partners to think about tackling different parts of that trip. After we complete Artemis 4 and start building that gateway around the moon, we'll start looking at how to expand our capabilities on the surface. And Artemis 5 is when we first expect to have additional capabilities on the surface, a small vehicle called the Lunar Terrain Vehicle. So now what I'll do is I'll walk through these missions briefly to just give you a sense of what these look like. So again, Artemis 1 was completed. We had a splashdown of the Orion on December 11th, 2022, so late last year, after that first test flight of the Space Launch System and the Orion crew capsule. That gave us some views like this. So I like to say that the farther away we go from the Earth, the more we appreciate where we came from. When you get a view like this taken from the Orion camera on the solar panel of the Orion, it kind of really puts into context, what the Earth is like out here in this broad solar system, universe. If you've ever heard any of the Apollo astronauts speak or been lucky enough to speak to them yourselves, they all have this way of talking about going to the moon, giving them this sense of awe about the Earth. All of the problems of the Earth could be basically covered with their thumb, and it really drove home to them this need to collaborate, to be partners, to take care of each other instead of to be in conflict. These are the types of challenges that we give ourselves that really drive that kind of partnership. How can we work together to meet these lofty goals for humankind instead of squabbling over who gets to do what? And so that's one of the things that always strikes me when I hear one of those Apollo astronauts speaking about their experience, seeing the moon, being on the moon, seeing the Earth from that perspective. And it's just amazing to see the Orion giving us that perspective again from Artemis 1. And we hope to have this as a routine part of what we're doing in the future. So I'll show a few of these for each of the missions. Mainly, I want you to see how much we are planning, right? So Artemis 1, again, was a test flight of the Orion. It flew out around the moon, orbited the moon, and came back so that we knew the systems would operate in a manner that was safe enough for us to have our friends be on Artemis 2. I like to say it that way, right? It's not we're putting our astronauts on Artemis 2. These are our friends. We know these people. They're part of our NASA family. And they're going to ride the Orion out around the moon. And so Artemis 1 was a critical step to make sure that we knew we had designed a system in partnership with our industry partners that could safely bring our friends home when we asked them to go out to the moon. Now on Artemis 1, we did some science. Just like I said, we have to learn about that environment so that we can plan for it. We had a series of sensors and studies inside the Orion that told us about the radiation environment, about the vibrational environment that the astronauts would be expected to experience, learning how to deal with some of that radiation. There was a vest that we put on one mannequin that flew out there so that we could compare the amount of radiation experienced by sensors without a vest versus sensors with a vest. We studied how biology responded to that deep space environment because we, human beings, the biology that we are, will be exposed to that exact same environment when we fly to the moon. We also tested out the ability to launch what we call CubeSats. So CubeSats are a shoebox-sized spacecraft of their own. They're great because they're small and they can go do whatever science they're designed to do. The hard part for them is getting there. They need to have a ride. And so this is not something we've done in the past where we have other small spacecraft that come off of a vehicle that we're launching for a crewed mission. And so it was kind of a test in itself to see if we could send some of these CubeSats out there. And so some of these have returned some science. Some of them have learned about what it would take to do this in the future. But in total, we're learning how to try to take the most advantage of every opportunity that we have to fly in space to learn as much as we can about that environment to help us prepare for living out there and working out there. Now, Artemis 2 is what we're planning right now. This will be another integrated flight test of the Space Launch System and the Orion spacecraft, as well as the EGS Exploration Ground System, except this time we'll have our astronauts on board. So the Artemis 2 crew was announced not very long ago, and in fact they just came through Washington, D.C. last week. I know they came here to the Smithsonian, but they visited many other places as well. These 4 people, again, to those of us that work at NASA, and probably some of you in the room know them as people, right? These are our friends. These are our colleagues. We work with them. We know them, and they are going to get to go on a very exciting adventure out to the moon for the first time in, again, over 5 decades. So, I really like to drive home give a face to this, right? This isn't just robots and vehicles going to the moon. These are people that we know. And they are going to be trailblazers in the Artemis missions to prepare us to be able to land other friends on the surface for Artemis 3. So again, Artemis 2 will fly out to and around the moon with our astronauts on board. We'll also conduct some other activities, proximity operations, demonstrating the ability to actually fly the Orion out around after it separates from the interim cryogenic propulsion stage. So that's the stage that kind of gives it the oomph to get out there to the moon. So we'll be learning. These are all steps that we learned through Apollo with the missions that led up to the landing of the Apollo astronauts as well. And so we'll be working on that through these flights, and this will help us really understand how our astronauts can respond in that mission flying out to the moon. So Artemis 2 will be followed by the 3rd mission, which will be our first landing on the surface. This will carry astronauts to the South Polar region using something now called the Human Landing System. So the Human Landing System is a vehicle that we will send out to the moon, and then the astronauts riding on the Orion will rendezvous with that vehicle, the HLS, in what we call the near rectilinear halo orbit. So that's an orbit around the moon that is fairly easy to maintain. And we don't have to work a whole lot to keep the spacecraft there. It's the orbit that we're going to start building the gateway in. So we're going to learn about that NRHO orbit. We're going to rendezvous the Orion there with the human landing system before they head down to the surface of the moon. And they will be the people who get a tremendous view that we've never seen before. This is really going to be a completely different location than what we experienced during any of the Apollo landings, which were mostly in the equatorial region of the moon. So this will truly be a new environment. The South Polar region is actually an exciting environment for several reasons. Being at the very bottom of the moon, the South Pole of the moon, puts them in a location where there are high ridges, high topography that has sun for far greater than the average amount of sun on the surface of the moon. Conversely, there are depressed areas, impact craters, any kind of depression that sees less light than normal. And that, we think, results in locations where we might see volatiles preserved, things like water, things that would volatilize if they see the sun. If that's there, then they can take advantage of it and use it in future missions. So Artemis 3 will go into that near rectilinear halo orbit, so that's the orbit kind of going around the moon from the north to the south pole, and that enables us to always see the Earth from that orbit. So anything on the surface of the moon that can talk to that vehicle can then also talk back to the Earth. And if you're down at the polar region, the south polar region, you should in general, depending on the sites we select, be able to see the Earth as well. I talked about the human landing system for Artemis 3. We have identified SpaceX as the company that will provide that. The Starship is the name for the vehicle that they've given for us to use. And here's an artistic rendition of what that will look like. So again, we're partnering with industry to help us build these systems. And SpaceX is testing out the systems that will eventually develop into the Starship that goes and lands on the surface of the moon right now. As they're working on that, we're thinking about what are the places that we can go to. So I talked a little bit about trying to be able to continue to see the Earth. Well, in the South Pole, we're looking for places with gentle slopes. We would like to be able to see the Earth continuously, at least from the beginning. Sunlight for the whole time that we're there. We're looking at places where the Lunar Reconnaissance Orbiter has collected high-resolution data so we can see that surface as we're coming in. Last fall, we announced 13 regions that we're looking at in more detail right now to understand where we'd like to land that human landing system for the first time in Artemis 3, and these are those 13 regions. We'll continue to work at that to try and narrow that down in collaboration with SpaceX as we move forward. Puts us in a position for Artemis 4 to follow that first crewed landing. This would also be a landing, but we will also test out our ability to deliver another element out to the near rectilinear halo orbit that will be added onto the gateway. So between Artemis 3 and 4, the first element of the gateway, the power propulsion element, which is basically the system that can move the gateway around and provide it with power, will be delivered there independent of one of our crewed missions. But for Artemis 4, we're going to carry out another element to be added to that. So that's us beginning to build that supporting station out at the moon in the near rectilinear halo orbit so that we can support crewed activities on the surface. Artemis 4 will also conduct a landing on the surface. And as you can see from these artistic renditions of what we're doing, these missions start to get more and more complicated, right? So as we're learning, we gain the confidence to do more with each mission. And that's what we're talking about. Learning about that environment so that we can begin to live and work in space. Artemis 5 is the last one I'll talk about today. This will be another crewed landing, but now we will also have landed on the surface something called the Lunar Terrain Vehicle. One thing we know is we'd like to go as far away as we can once we're on the surface, and to get farther and farther away, we need some help. So we're going to have a vehicle. The Lunar Roving Vehicle was what supported the Apollo astronauts in what we call the J mission so that they could go many kilometers instead of just as far as they can walk. And it's the same concept here for Artemis 5. Again, continuing to increase the capability that we have. So here you can see we're continuing to build up the gateway. We have missions now that are starting to reuse vehicles on the surface of the moon, that LTV. This is how we start to build up infrastructure on the surface of the moon. By leaving things there that we can reuse, we can start to spend more and more time on the surface of the moon. Our initial missions, we expect to be about a week, 6.5 days on the surface, but we would like to build up to being there for about a month, once per year. Again, slow steps, learning as we go, partnering with industry, partnering with our international partners to learn how to live and work in space. Just last week, we announced a lander that we would use in Artemis 5. This is the second lander. This comes from Blue Origin. They're calling it the Blue Moon. So this would give us 2 vehicles that can land on the moon, each with their own unique capabilities. So as we look forward and think about it, there may be times that one is more useful for a different landing site than another, and we have more robustness in our system. Again, partnering with industry to help us go and explore the surface of the moon. So then the question is, what comes next? Well, I talked about things like the gateway in the top center, and we'll continue to build that up. We have rovers and vehicles on the surface. Maybe we have power generators on the surface. The bottom left there is showing an example of something that we call in situ resource utilization. I talked about the fact that there could be ice on the surface. Can we use it? Can we use any other elements that come out of the minerals in the surface rocks and regolith, basically the dirt of the moon? These are all things we need to learn as we go, right? Learning basically to live off the land, and by reusing the hardware that we're sending, we can start to develop a system, a process, operations, infrastructure, habitation, transportation that enables us, again, to do that step, learning to live and work in space. How do we do this? Again, go back to the very beginning of my talk. By developing and understanding objectives that the broad community has, we'll know which are the right things to do next, so the biggest amount of that spectrum of participants can move forward, can start to realize the vision that they have for going to the moon. One thing that we're working on is called the Artemis Accords. This is helping us to develop partnerships back here on Earth. Again, the more we do out in space, the more we learn and grow here on Earth. So the Artemis Accords is basically identifying, common practices or principles that we think we should all work with when we're on deep space, in deep space. And so what I like about this is this is not space agencies, this is countries, right? And so some of these countries are not providing big elements, but they want to be a participant. So they're going to work with us to identify what are the right things that they can do in the system, even if they can't provide something very big. So then after the moon, the next big step is going to Mars. We have to learn how to spend more and more time. So going from 6.5 days to 30 days, that trip out to Mars is a long one. And some people like to say, well, geez, it seems like it's going to be forever till we get to Mars. Well, we are at Mars right now because we have robotic missions there that are already starting to capture the data that we need in order to understand what we'll have to develop for people to survive there. So that's one thing I like to make very clear is this is a process, an iterative process of learning, just like I described for the moon. But for Mars, we've already started that. And we want to get there. It will take us learning through many, many missions, many of which we've already conducted. We've sent orbiters, landers, rovers, and we continue to do that and learn more about that Mars environment. The architecture we're developing actually has some commonalities. And so that's one of the things we're really trying to look for as we think about how to go to the moon is what are some things that we can build for the moon that we might also need when we go to Mars. The tricky part about Mars, I talked about a few months to get out there. Well, a full round-trip mission to Mars will take between 2 and 3 years. Okay, it's months to get out there, and then it depends how long you want to stay, and then it's many months to get back. So it's not something where we can go and say a month in, like, oh, maybe we shouldn't have launched just yet, or we need to change something because we won't have time to do that. So we have to learn about these systems in low Earth orbit, at the moon, around the moon, spending more and more time out there in deep space so that we can be prepared to take a long trip to a place like Mars. And so with that, I've got one more video. This is CHAPEA. This is a test that we're about ready to start here on Earth. It will start in June, and this is starting to simulate what a long-duration mission at a place like Mars would be like. So we can simulate a habitat with living quarters, work quarters, even airlocks and hatches that take us out onto the surface of the Mars. So we can start thinking about how we plan daily operations. What is it like to deal with the food that we'll have there? So for instance, the food that we take to Mars will probably be there before our astronauts get there, because we need to know it's there. We don't want to send them there if the food's not going to be there. And we can't just send more over and over for them. So we have to learn how all these things work here on Earth, and here on the moon, and here in low Earth orbit, before we can take that big step to Mars. And so that's what these ground studies are all about right now, using the Earth to learn how to take those big steps. So to conclude here, I just want to bring this back around to the thing I said at the very beginning. We are the Artemis generation now, okay? These bold adventures, these bold endeavors that we're undertaking, it's all of us. NASA's working to understand what the community needs or would like to see. What are your goals? Why do you want to be out there? Because we need to know what that is so that we can make the best choices possible for our next investments to enable us to move forward to the moon and onward to Mars in the future. There are plenty of opportunities out there, plenty to do. Industry has lots going on supporting us. NASA has jobs. The international partners are working on it. I get asked all the time, what do you got to do to work for NASA? The answer is very simple. Figure out what you love to do, because I guarantee you somewhere across the spectrum of who's working on this has a job that probably lines up with that. So with that, I think I am done. I really appreciate the time and the opportunity to talk with you all today, and I'll answer any questions we have.
Thank you very much for that insight into how all of these pieces, all of this complex architecture is coming together to give us a pathway back to the moon for people. We have some questions that have come in online, and I'm going to take some questions from here in the room. So if any of you would like to ask some questions, please feel free to come up to the microphone. We'll start from one that we've received online. If you use the Starship for the HLS, that's a very tall ship. After landing, how do the astronauts make their way from the crew cabin down to the surface? And also, do you have to find a really flat place to land that? Because it does seem sort of top-heavy.
Yeah, that's a great question, and that's part of what we're working on right now, is trying to understand exactly what we need to look for on the surface. So like most landers, you do want to have a nice, flat place to land. An airplane here on Earth, you don't want to land on a big rocky patch of Earth with high slopes either, right? So the vehicles that we're developing now, we're going to learn how they perform, and we're going to learn what those landing sites need to look like so that we can go find them and do that. But yes, very flat, smooth areas is one of the main things that we look for. On that specific vehicle, the concept that SpaceX has presented to us has basically like an elevator that takes the astronauts from the top down to the bottom. And then they can go do their work and then ride that back up.
Let's take a question from here in the room.
Great, thank you very much for the presentation. On radiation, can you talk about what is the maximum time right now? You mentioned the testing with the vest on Artemis. Where do you see the timeline in regards to the development that's needed to go for long-term missions to the moon and Mars?
Yeah, so it's a really good question, and it's a complicated answer, because as we develop technology to help protect ourselves from that radiation, the target we have for how much radiation you can tolerate will change. And also we learn how to deal with how the human body and biology in general responds to that radiation environment. It's definitely a focus for us studying. First, we have to understand what the radiation environment looks like. So leaving low Earth orbit, going outside of the magnetic field, we have to understand what that environment is like at the moon, because spending 6.5 days is different than spending 30 days, which is far different than spending months. So we have to know what that looks like. there are solar events that increase the amount of radiation you may be exposed to. How do we detect those and protect ourselves from them? It's almost like we need a space environment, like a weather system. And in fact, that's what our science mission director at Heliophysics division does. So they kind of monitor the sun, they study the sun, but part of that knowledge is understanding what the sun is doing into the solar system. So all these things work together, science and technology and engineering together to help us understand how to explore. So I can't give you an exact answer to your question, but I think what's interesting is to think about the complexity of that problem and how we're trying to work on it right now.
When you think about someone traveling to Mars, you're thinking about the amount of radiation that they take on a round trip there, but they're not going to go twice.
Yeah, you would think that it would be one trip, right, for an individual. When it's low Earth orbit, we have astronauts who flew on the shuttle many times, astronauts who have gone to the International Space Station more than once. And we have to learn how to kind of calibrate. This feeds off that prior question about that radiation environment. It may very well be that astronauts going on those first trips to Mars only go one time. And if you think about it, that's like a 2 to 3 year investment of your life. That might be okay with some people, but eventually, we're talking about living and working in space, right? So at some point in the future, a vision we have may be that people live on the moon and people live on Mars. Now, is that going to happen in my lifetime? I have no idea, but we're on a path to help enable that if that's the direction that we're going to go. Yeah. And so we're trying to learn those things now so that we can make decisions about exactly what your question was.
And managing the radiation, of course, is a huge part. Is the future plan for running Mars missions concurrently with an ongoing lunar campaign?
Yeah, that's a good question. There are a lot of potential ways for us to think about that. Right now, what we mostly focus on is kind of that first mission, right? So we're planning several missions out on the moon so that we know what information we need to collect, one, to be able to spend more time on the moon, but two, to kind of set the stage for how you even do that first mission. Once you do a first mission, then you have options. And so we haven't narrowed down what those options look like beyond that first mission. Right now, we're really trying to support how and what data we need to collect to understand so we can do that first mission to Mars.
Yeah. I think we have another question here from one of our guests in the room.
Yeah, thank you. So I was wondering, what does low Earth orbit is my first time hearing the word. And then the other one, what does a country need to do to express their interest in participating in the Accords?
Yeah, so low Earth orbit is where our International Space Station is. So it's obviously off the surface of the Earth, but it's within a protective envelope that we have, our magnetic field. So the Earth is like a big magnet, has a north pole and a south magnetic pole, and it creates a magnetic field, and that magnetic field helps deflect basically energy from the sun. So that energy from the sun goes around this protective envelope, and it's really one of the key reasons that life is here on Earth as we understand it. So the International Space Station gives us experience living off the Earth in space, but we don't consider that to be deep space. So you kind of have low Earth orbit here. If Ross is the Earth, you've got low Earth orbit here, and you have a protective barrier here, the magnetic field, and then out there is deep space, and the moon is out there. So we're learning here about how to live off the Earth so that we can take that trip and learn more about that environment and spend time out at the moon. So that's kind of what the low Earth orbit thing is all about. And so for international partnerships, the Artemis Accords are open to be signed by any international partner. And we do engage internationally as an agency, NASA, to look for partners who are interested in doing that. So there are often countries that are engaging with us and exploring their options with respect to the Accords, which again are basically kind of like guidelines or principles that we would agree to, that if we're all working in space, these are, it's kind of like the golden rule, like here's how we treat each other to do a good job out there.
Thank you.
And everybody's good at something, and they have that unique capability that they're able to contribute. Another question from the room here.
Kind of got two questions, all logistics. So Artemis 3 SLS Block 1 with Orion goes to NRHO and gets off onto Starship, onto the moon, and then Starship leaves the moon and goes back to our NRHO, goes back onto the Orion capsule. What kicks Orion out of NRHO? And then also, are we doing an Aldrin cycler on Mars, or are we going to have a Martian gateway equivalent, or are we just going to do single-shot missions to Mars?
So let me answer the first question, and then I might need you to re-ask the second one, so don't go far away. So the Orion will be in orbit. You know, if this is the moon, this NRHO goes around the North Pole and then down far around the South Pole. And so what happens is the HLS will leave the moon and catch up to and connect with the Orion. The Orion will then be able to depart that orbit on its own. So it has the capability to kick itself back, but it's going to be in that orbit, so you can kind of, you know, if this is where, this is not my area of expertise, and I love the physicists who work these, you know, complicated mathematical problems, but it's kind of like a slingshot to send yourself back to the Earth. And can you repeat your second question?
Yeah, to get to Mars, are we going to do like a Aldrin cycler where you have multiple ships going in a huge, long orbit and you're only catching a ride from Earth to Mars and then letting that ship go around? Or are we going to do single-shot missions to Mars? Or are we going to have like a gateway around Mars that we will then meet up with?
Yeah, so, you know, kind of Ross was alluding to some of the options, and you just cited a number of possible options for ways that we could approach going to Mars. An initial mission is most likely to be kind of a single shot, but when I say a single shot, we're probably going to go and pre-deploy things. We're not going to be able to carry everything with us, and I kind of alluded to that when I was talking about Chapea. We'll probably take food and supplies and pre-position them on the surface of Mars so that we don't have to carry all that with us. But the crew itself will probably fly out there in a single mission from the Earth over to Mars and then come back.
Cool. So Apollo style.
Yeah.
Awesome. Thank you.
Another question from our online audience. What is the selection process like for the astronauts who were chosen from the Artemis mission? What makes the best candidate for this? In other words, how do you get that job?
Yeah, so I'm not an astronaut, so I'm probably not the best person to try and answer that. But, you know, the astronauts, you know, this is why I try to say things like I refer to them as our friends, right? They're normal people, right? They're ambitious people, and they're good at a lot of things. So there is no one thing that makes you an astronaut. In this group, this Artemis 2 group, we have pilots, we have scientists. There are a number of different ways to get there, but I think some of the more important things are, you know, being able to work together well with teammates, right? Because we talked about some of those hazards to human spaceflight, being in small areas. If you're going to be in a small area with 3 other people for a long period of time, you better be someone who's good at getting along with each other, right? And you got to be able to help each other out and fill in for each other. So it's a really kind of a broad skill set of things that you need to do. You can have a fundamental, you know, like number 1 capability. You can know how to fly. You can be a scientist. You can be an engineer. You can be a doctor or medical, you know, but it's not any of those one things that makes you an astronaut. It's the whole package together that helps identify these folks.
Everything you're going to need in 6 months, all within a group of 4 or 6 people.
That's right.
Like that. We have time for just 3 more questions, which we'll take from the room.
Thank you. That was
do it first.
Presentation. My question was about gravity on Mars. I guess this is the later stage of these projects, but how is that being taken into account, especially because here we're talking about longer periods on a planet that has, I think it was in the presentation, 3/8 of Earth's gravity, and how is that going to impact health and mental and physical of those who will be joining? Thank you.
Yeah, so the first thing I want to say, so the question, just for everybody heard, is how will the gravity of Mars impact the crew on a mission there? And so the first thing I want to say is all the questions you just asked are the questions we're asking ourselves right now, okay? And that's why it's so critical for us to go live on the International Space Station and go live on the moon and go live in deep space on things like the Gateway so that we can begin to learn how we will deal with that at Mars. So the moon is less gravity than both Mars and the Earth, about 1/6. So, but it's interesting things to think about. So one of the things that we think a lot about is the gravitational change. So if you go spend 6 to 8 months flying out to Mars, how quickly can we expect our friends to be able to push the right button or pull the right lever once they've landed. If you think about this is why we fly long missions here on the International Space Station now, spending a year up there and then looking at, what happens when they come back. So here on Earth, when they come back, they have, if you've seen pictures of them, they have a little entourage with them, right? We're supporting them and helping them. But when they go to Mars, as Ross just said, it's them, right? And they're going to have to rely on each other. So knowing how, and that's the kind of information that helps us decide, how to build those systems. What can we expect them to do in the short term versus what we have to automate once they get there? Those are all open questions for us right now, and understanding how gravity will have an impact on them. It's just like the radiation that we're talking about. This is why it's one of those hazards that we need to understand more about. And again, we do that by living on the International Space Station, by living at the moon, by living around the moon. That helps us prepare to take that next step.
Okay. And just two more questions. So our next guest here in the room.
Hi. How long does it take to plan a mission, and how long will it take to plan future missions?
Ooh, that's a really good question. It takes a while. It takes some time. So it can take years. And sometimes we have to build the hardware, which can take years to even, I don't even know, over a decade in some cases. So one of my favorite things about watching Artemis 1 launch, I was working at the Kennedy Space Center supporting that, mostly interacting with the media throughout that time period. Often at nighttime, though, I had some time off, and I liked going out to the launch pad and just kind of sitting there, by myself, half an hour, 40 minutes. And the thing that I loved about it was watching people come by. Everybody who's worked on this thing for over a decade in some cases, some just months. But it was kind of neat to watch them, say goodbye to a friend, right? Because this thing was, sooner or later, was heading up off the Earth. So planning a mission from start to finish can take months to years to a decade, depending on what you mean by that mission. The Artemis 1 mission, the time we started building some of that hardware was a long time ago, many years ago. Planning the mission itself, Artemis 1 specifically, a few years probably. And as we go forward, we hope to get into a cadence, a rhythm, if you will, where we're doing this about once per year. And so we'll probably be planning a landing 4, 5, 6 years ahead of time once we start getting good at this, right? But you'll have a landing each year. So at any given year, you're planning 5 years out for a landing, and 4 years out for a landing, and 3 years out for a landing, because we want to get into that rhythm so that we can spend more time there and help answer all the questions that I've just been asked here today. So that's kind of how mission planning works. And sometimes things change during the time period that you're planning, so you have to kind of replan some things, and it can take a little longer. But that's what the process is for us, is learning, adapting to what we're being asked to do, deciding what we need to build, how to design the operations to go do it, partnering. Those things, they all come together. It's a constant cycle for us. An individual mission, though, can take years to plan.
Well, we've reached the top of the hour. Let me just take one more opportunity to thank Dr. Jacob Bleacher for an outstanding presentation and for sharing your wisdom and insights with our audience. Thank all of you as well for being here tonight, and to our online audience for joining us here. You are the reason why we do this, and so thanks very much. I'd also like to thank our sponsors, Aerojet Rocketdyne and United Launch Alliance, for their support for this lecture series. Without them, we wouldn't be able to do this. We have stargazing that's available outside until 10 o'clock, so please feel free to take advantage of that. And the final talk in the Exploring Space lecture series will take place on June 29th, when Dr. Amanda Hendricks from the Planetary Science Institute will talk about the habitability of worlds in the outer solar system, reaching out beyond some of the places that we've been talking about today. So thanks to all of you for being here. Good night.